Last lecture, I had a momentary brain problem. One of you who's not here actually came and told me, I was like, oh, yeah. We were talking about how to transform tree satisfiability to subset sum. And it was this magical of 4, right? And why? Well, the 4 is on, you basically create one number per each possibility, right? Per each variable, 2 per variable. One for positive, one for negative, one for true, one for false. Then you put here your conjunctions. And what is going to happen is that here you want ones, right? You're going to require ones here, which means either this or this has to be chosen, right? Either this or this has to be chosen. Now, the thing is, once you do that, what's going to be the sum of this thing, right? It could be, it has to be at least 1, right? But it could also be 2, it could also be 3. Because what you don't know is whether you're going to make 1 true or 2 true or all 3 of them true. So what you do is you put these things, right, 1 and 2 here on each one of them so that you end up with 4 regardless. So you could happen to just choose one of these true, and you would end up with 4 by choosing these 2 guys. If you happen to make all 3 of them true, so you would have not x1, x2, and x3, then you would only choose this guy to make it add up to 4. So by this making that up to 4, right, you are requiring, if you look at every one of these rows for the conjunctions, the columns for the conjunctions, you're going to have 3 ones in there, right? So by doing this, you allow for 1, 2, or 3 of those to be true, which is what the subset sum would do. Right? Why didn't they choose 0? But yes.
Stop me if I'm the only one, but could you start that from the very top?
Could I start that from the very top?
Does anybody else need that?
Yeah.
Okay. We have a tree satisfiability. What does that mean?
Oh, that's a great question.
Yeah.
Given a Boolean function,
We have
find the satisfiable combination.
Conjunction, or we have a conjunction of disjunctions, right? Conjunction of clauses. Each clause is a disjunction. And each disjunction, each clause, has how many variables? 3. That's why it's tree satisfiability, right? As opposed to other kind of satisfiability. Does that make sense? Now, sorry.
And by conjunction, you mean like ands and disjunction?
Conjunction is
ors?
and, disjunction is ors.
So
yes.
Down arrow is or, up arrow is and.
Down arrow
Or.
is or. The way that I remember them is union and intersection.
Oh,
Down
okay.
arrow is U for union. Well, it's not U, but it's the same way as the U.
Okay.
So this is or, and then up arrow is and.
Got it.
Yes. Cool. Thanks for asking the important question. So what we are trying to do is to reduce tree satisfiability to subset sum. To basically show that if I have a satisfiable formula, I'm going to have a subset sum, right? And if I have a subset sum, I'm going to have a satisfiable formula. The way that we do this is by cheating and creating a bunch of numbers, right? And then we're going to do the subset sum.
Could you go over subset sum again?
Subset sum is given a set of numbers and a set of subsets, right? Given a set of numbers, can you find a subset that adds up to a given number? Given the numbers 1, 2, 3, 7, 9, can you find a subset of that that adds up to 16?
Okay.
Examples are great.
Yes. So that's the subset sum problem, right? Cool. So what we're trying to do here is cheat and create numbers so that subset sum is equivalent to 3 satisfiability. We're going to do that by creating numbers that have a gajillion digits, potentially. We are going to create one column, one digit, right? One space per variable. And in this case, this example, we only have 3 variables. We could have way more than 3, right? And then I'm also going to create one row, one digit per clause, per disjunction. Does that make sense? Then I'm going to create 2 rows, 2 numbers per variable with the corresponding digit set to 1. So what I'm saying here is either this one is going to be or this one is going to be. And then for each one of the clauses, I'm going to put a 1 if it includes the variable. I'm going to put a 1 on the x1 or the not x1, depending on whether it includes the variable positive or negative. Does that make sense? And so what I'm going to do is, well, I'm going to require my sum to have 1s on the columns, on the positions corresponding to the variable. By requiring a 1, I require, right? By requiring a 1 here at the leftmost thing, I require that either one of these numbers, right? Either the row with x1 or the row with not x1 is chosen. Does that make sense? Cool. Now, what I really want to require for the other ones, for the clauses, is that at least one of these ones is chosen, right? So what I want is the sum to be either 1 or 2 or 3, right? If you just look at the ones above, right? What I'm going to do, since subset sum doesn't let us do, right, ORs, is I'm going to add 2 rows per clause with 1 with a 1 and 1 with a 2, and zeros all over. So the first 2 rows under the blue arrow are for C1. These 2 rows. Yeah.
I think you ought to do the line with a line through it, top left.
Yeah.
That didn't work.
Maybe. I selected the wrong thing. I meant to do this. Ah. So these 2 rows are for C1. So one of them has a 1 and the other one has a 2 on the corresponding column for C1. What this enables me to do is to require 4 as the value, right, for C1. So what does that mean? I need to choose at least one of those, because if not, I could only reach 3, right? But I can choose either 1 or 2 or 3 of the rows that match this clause. Does this idea make sense? Do you see the cheating? Do you see how it works, right? And each digit, since you're never going to have carryovers, you're doing it in decimal, right? You're never going to have carryovers, so each digit is completely independent of each other. They are officially numbers, but you can also see them as just strings of stuff or arrays of digits, because you're never going to have carryover, right? And so, if I have a satisfiable solution, right? If I have a satisfiable assignment of variables to pre-sat, I am going, right? I can just choose the numbers for that. So if I chose x1 to be true, just choose that one, right? If I chose x2 to be false, I'll choose not x2. And if I choose x3, then I'll choose x3 rather than not x3. So you choose the numbers, and then just choose from these other dummy ones so that you add up to 4 here. And they are all independent, right? They don't have anything on any other thing, so it will always work.
Since you're using disjointed, like C1 is not X1 or X2 or X3, I mean, theoretically, couldn't you just have one of those three have a one value in that column, or you still have to have all 3 of them?
I don't have all 3, I just need 1, which is why I do this. Imagine that I only have not x1, right? So I'm going to choose this guy, and then I'm going to choose these other 2 rows, 1 and 2, to make it add up to 4, because I only had 1.
Right, gotcha.
But I may have all 3 of them.
Okay. But even if you had all 3, it's still...
If I have all 3 of them, I just choose this guy with the 1, and I'm good.
Okay.
Right? And if I had 2 of them, then I choose this one with the 2, and I'm good.
Okay.
What these dummies let me is...
Keep it consistent.
Yeah, because I need 1 target, as opposed to say 1, 2, or 3. And so, if I have a satisfiable value assignment, then I can immediately come up with a subset of numbers that will add up to this. Does that idea make sense? Do you see how? Do you see that it works? Yes. Do I have as many numbers as clauses, or do I have more? I have more, right? Way more. But it's still a polynomial value based on the number of clauses, right? I have 3 clauses, 3 variables. I'm going to end up with 1 number per variable, right? And then, 2 numbers per variable, and then 2 more per clause. Conversely, if there is a subset sum, then I will have a satisfying assignment of variables, right? Once I get the subset sum that adds it, just go looking in this, right? And choose the corresponding number. So if this number was chosen, 10010, the first number, then that will mean that x1 is true. And I can only choose one of them because my target is 1. And I have to choose one of them. So for every variable, I will have an assignment to either true or false. Does this idea make sense? Yes?
I'm getting there.
Close enough.
A lot closer than it was on Monday.
Cool. Well, on Monday, I didn't even know what it meant. Any questions about this that you can verbalize?
So we have 444 down on the bottom right.
Yep.
And I see that you padded it so that we only choose one of each.
I can choose either 1 or 2 or 3 for each clause.
Okay. So I guess my question is, say for example you chose x3, not x2, and x1.
Okay, so we chose let me do where to go. So we chose x3, right?
Mm-hmm. Not x2.
Not x2, and then x1. Right? As numbers or as value assignment?
As value assignment.
As so it's a satisfying conjunction,
Yes.
right?
You would end up with a sum greater than 111,444.
Why? How? No, right?
No.
I have on the C3 column, I have 1, right? I actually, in order to make this into a subsystem, I have to choose the last 2 at the bottom. 1, 2, and that gives me 4.
Okay.
Right? On C2, I have 3. So I have to choose the guy
So
with the
you
1
can-
on C2.
You can choose to only take one of those. On the
Yes,
bottom half.
yes, yes,
Okay.
yes. It's a subset. So,
Got it.
right? Yes. I could choose, I need at least 1 because I need to get to 4s, but I don't need both of them. I don't necessarily get both. So what they give me is the degree of freedom of how many of those have to be true.
So do you have to choose from that subset?
Sorry?
So do you have to choose from below the blue line?
I have to the way they did it
Okay.
because I need
So
4.
if they didn't implement, if those are all 3s at the bottom, you can choose not to choose.
Yes, but I think, yeah, but I don't know if that wouldn't work because then I could just choose 3. I could just make 3
I see.
with
I see.
the ones at the bottom.
I see.
I could maybe choose 1, 1, right? Maybe, but I don't know.
Okay.
But I wouldn't want to prove it. I'll just believe the guys in the book.
Fair enough.
But yeah, that's why you need at least 1. Yes.
Okay, or the same case, rather than not x, x2, if we choose x2, okay, what is going to be right there?
What's going to happen?
We
And
don't have-
assuming that my clauses are right, correct.
Well, nothing satisfies C3.
Oh,
Yeah,
notice satisfies C3, so I will never be able to do this. Right? That's not a satisfiable. That doesn't satisfy my clauses. It cannot be a solution, right? I will never be able to get a 4 for C3. So basically, the argument is these are the same-ish problem. If you solve one, you can solve the other. It's not they're the same. If you solve one, you can solve the other. Does that idea make sense? Yes. And we did this for 700 problems, and by now they should blur, right? You need to, first of all, read the book and pay attention to each one of them, and then maybe make memory aids or kind of, right? Make sure that they don't blur by the time of the final. Yes.
So is there a generalized n satisfiability problem then?
Yes, yes.
So would subset sum work for that as well?
Well, what
Expand
we
it the
did
same way.
before is that normal satisfiability reduces to 3 satisfiability. I think. No. Basically, you can reduce normal satisfiability to 3 sat, but I don't think we have done it.
Okay.
Yeah. Satisfiability without the 3, right? Basically, what you can do is come up with more clauses. If you have a clause that has 5 variables, you come up one with 3 and then, right? Oh, can I do that? No, not directly. I need to do more stuff, right? So if it's 1 of 5, can I do... Can I transform it easily, right? Let's see, can we transform satisfiability to 3 sat? If we have more, we can just add, if we have less, we can just add variables. If we have more, if I have 5, either one of these 5s, right? Can I do with a conjunction? What
Or
can
I guess
do?
to any of these, like if it was 5 satisfiability, do any of these still apply? Can we do like 5 color ability?
Not necessarily. You need to come up with, right? You need to come up with a transformation. Maybe people have, but in general, no. If you change, this is math. It's like code. If you change one assumption, right, then maybe the whole thing still stands, or maybe not.
Okay. And does 3 satisfiability always have 3 disjunctions and 3 conjunctions?
No, it has all your clauses have 3 disjunctions or 3 variables in the disjunction. That's the requirement. You can have as many conjunctions as you need.
Okay.
That's the size. We can go Google. Yeah, SAT is NP complete, so 3 SAT is also NP complete. Haha. There it is. To reduce the unrestricted SAT problem to 3 SAT, transform each clause to a conjunction of n-2 clauses where I have L1, L2, right? Oh. Basically, I have this, right? I'm joining them with this x2 variable. They have not x2 on the other one. That's the trick. That's the transformation. That will convert a SAT into a 3 SAT. But you cannot, in general, do those things, right? I mean, we know that, right? We have this, so now we know that 3 SAT and 4 SAT and 5 SAT is. But like, we had assignment and we have pairs, right? Matching. then 3D matching is actually NP complete, whereas matching wasn't. So 4D matching, I don't know. I'll need to. And actually, when you start looking at that stuff, it's like, there is a precise definition of the actual problem, because there may be 7 different ways of defining it. Some of them may be, some of them may not. So. This is the guy that defined all of them, and he did this bunch of stuff. We have shown these ones, right? This is probably a good thing for studying, so you at least recognize the problems. Now, I probably have downloaded it 7 times, but I'll download it again. Oh, no, I didn't. There we go. We have seen that 3SAT reduces to all of them, right? And vice versa. We talked about decision problems versus minimization versus search, right? So a more formal definition of a decision problem is a problem X is a set of strings. So we define a problem as the answers, right? So it's a set of strings. An instance of a problem is one string, and the algorithm A solves problem if when you run it on the string, you get yes if the string is in the problem. So we are defining the problem as a set of strings. If you're doing theory of comp, you'd recognize that, right? It's a decision problem. It's recognizing a string. It's a string in a set. It is the exact same definition, but now instead of just doing automatas or Turing machines, you have a real programming language. And the algorithm A runs in polynomial time if for every string S, A of S terminates in at most P of the absolute value or the length of S, right? Steps, where P is some polynomial function, right? Length of the string is 100, maybe you do n squared or n cubed or n to the 27. So finding whether a number is prime, right? There is an algorithm that will do it in 8. The length in digits to the 8th power. P is the set of problems. Now we are going one level up, right? P is the set of problems for which there is a polynomial time algorithm. Now we are going to try to define NP. Rather than let's restrict it a little bit. Rather than one that will tell you whether a string satisfies, we are going to allow for cheating. We are going to allow for a witness or certificate, right? Basically, somebody is going to give you the solution. And so now your algorithm is simpler your C of ST is a certifier for a problem X. If for every string S being in the problem means that there is a string T such that you're certified with S and T will yield yes. T is here's the solution. Does that make sense? So rather than me having to go find the solution, I just verify that that solution is true, right? Potentially. I could cheat. For simple problems, I may say I don't care what T is, I'll go find the solution because I know I can do it in polynomial time, right? But does that gives us more power, right? Are these problems easier than P?
So all this is saying is that T is a bunch of strings within X, and it's comparing S.
T is
against
one
T.
string. T is one string. S, and actually T doesn't have to be in X. S is in X, and T could be a completely different string, right? So, for example, right, if I had the reverse of prime, right? If I had is not prime, is composite, right? As a problem, right? So how do you know if a number is composite? Well, you need to go through everything and see if it will divide it, right? Primes is actually harder. Primes is give me all the prime factors. So what can you give me as a witness? Just give me a number that divides, right? And so my algorithm, my certifier now becomes a lot easier. I just check. Does the witness that you gave me divide the instance of the problem that you gave me, right? So your T is a different string, maybe over a different alphabet, maybe over, right? Your T is sort of a solution or a witness that the solution exists, right? I tend to think about it more as the solution, but it's not always the solution. Maybe a piece of the solution, right? Maybe. And so we define NP as the set of problems for which there is a polynomial time certifier. So we require that the certifier, right, algorithm is a polynomial time algorithm, and also that the certificate T is of polynomial size on S. So you can't have a T that grows, right, too much. T can grow, but it has to be polynomial. And especially for those of you who are taking theory of comp, right, NP stands for non-deterministic polynomial. Basically, the idea in theory of comp was to say, oh, if you could try every possible solution, right? So if you could try every possible T at the same time, it would be polynomial. With the same idea of like non-deterministic automata. So the question is that easier? And the answer is, we don't know. Which is the question, is P equal to NP, right? P is decision problems for which there is a polytime algorithm. NP is the set of problems for which there is a polytime certifier, not necessarily an algorithm. As an example, right, is S composite. The certificate may be just a factor of S, right? So if it is composite, I will have it, and the length of T is less than or equal than the length of S, right? So, and my certification algorithm is just, or my certifier is just, does it divide, right? So composite is a number composite is in NP. Actually, composite is in P too, right? We have a polynomial time algorithm for checking whether a number is composite, right? For something like satisfiability, right? The certificate would be assignments of truth values to variables, right? So x1 equals true, x2 equals true. That's a certificate, and my certifier just checks, right, that at least one of them in each clause is true. So SAT and 3SAT are in NP. For the Hamiltonian path, this certificate may be a permutation of the n nodes. And I just need to check, first of all, that the permutation actually contains all the n nodes exactly once, and then there is an edge between each pair, right? So Hamiltonian path is in NP. In a way, right, if you think about how you'd go about programming this, right, if I ask you which one would you rather program, the one that finds the Hamiltonian cycle or the one that verifies given the witness, right? So in a way, it is obvious that verifying is easier, right? But what we are going to see is that in another way, we cannot say that it's easier. It's going to take you about the same amount of computational effort. Well, actually, we don't believe so. We see that, of course, it's easier. So we assume that P is not NP, right? But maybe we haven't been able to prove it. So NP is the set of decision problems for which there is a polynomial time certifier. And so we have tons of these problems, right? And then we start with philosophy and NP, right? NP captures vast domains of endeavor seems to roughly delimit what mathematicians and scientists have been aspiring to compute feasibly. Now we have EXP, decision problems for which there is an exponential time algorithm. P is a subset, maybe not a proper subset of NP, right? If you have a problem in P, so there is a polynomial time algorithm for just the string without a witness, right? So what I can do is just use the empty string as my witness and just compute that thing, and I get yes or no. Could also just choose any string as my witness and say yes regardless, right? Does that make sense? So I have a polynomial time. Now, there is another claim that NP is a subset of EXP, the decision problem for which there is an exponential time algorithm. So how can we prove that that is true? Well, I'll just generate every possible string in T, right, which is exponential, and run the certifier, since the certifier is polynomial, the total running time is some exponential function. We also have a theorem that says P is not exp. So we really don't know where NP lies. We know that exp is bigger than P.
Wait, I'm sorry, because it says here that P is within the NP, and NP is within EXP, therefore it shouldn't,
They are,
I'm confused.
that symbol is weird. That is proper subset. It is this symbol
Oh, it is?
with the, no, it is that symbol with the, with the,
Yeah.
with the equal part crossed.
Okay.
It's a proper subset, right? Yeah. Let's go verify that I'm not lying to you. Right now.
So what's the difference between a subset and a proper subset?
A subset, right, allows for the possibility that the two sets are equal,
Okay,
right?
okay.
So the set of all,
So a proper subset would be that it's a subset within it, but they're not equal.
exactly, it's a subset, but there's at least one missing,
Gotcha. All
right? And in math, most of the subset stuff includes proper subset. It's basically less than or equal versus less than.
Gotcha. All right. That makes sense.
Yeah, and so this is, yeah, they couldn't find the right thing. It's the equal is crossed,
Yeah.
but my font sucks. Or something. It's crossed the wrong way.
I'm good.
So we know that P is a proper subset of EXP. We don't know whether it's a proper subset of NP. We know there is a subset, but we don't know whether they're equal or not. Is P and P, right? Well, how could we solve an instance of 3SAT with n variables? Brute force it, do exhaustive search, right? Try all the 2 to the n truth assignments. Question is, can we do something better? Not just better for this particular problem, but better in general. And not just better, but really, really better, right? Supposed to, we can do better stuff that it would get me half or a quarter, right, of the time, but it's still exponential. I'm still doomed. It's just that I can run it on a Raspberry Pi and be doomed as opposed to be doomed on an i7. But I'm still doomed. Whereas if I get it from exponential to polynomial, that means that now I can actually run it on a computer, right? As opposed to I'm doomed. The conjecture is that there is no polynomial time algorithm for 3SAT. That's what most people believe. However, we do not know. Like, we don't know, right? Haven't proved it. So, if P equal to NP is the decision problem as easy as the certification problem, right? We believe, or I believe, and most computer science people believe, that this figure on the left is true, right? P is a subset of NP, and NP is a subset of EXP. It may be that we have the figure on the right where P equals to NP. Whoever discovers that algorithm, right, would become a gajillionaire. First of all, they would become a millionaire because there is $1 million prize on proving whether P equals to NP or not. And then they would just, right, get a gajillion startups that solve, right, have the interesting problems known to mankind.
It looked really good on the resume.
It would look really good on the resume. Yes.
What do you think, what is your personal opinion? Do you think NP is also NP?
P is not NP. And that's because it's a human thing, right? It's like, chances are we have been searching, right, for this for 50 years, right? Like people have dedicated their whole careers to this problem. Also, every grad student, right, spends between half an hour and half a semester playing with this stuff, right? Because, well, it's $1 million prize, right? And like all the time, when you see, many times you don't play with it when you see the algorithms class. You play with it when you get an optimization problem and say, let me try to solve it, right? And you don't realize that it's TSP, right? Or something like that. And so you go and spend a week or two trying to solve it, right? Till you realize that, no, I'm doomed. There is no known way to solve it. It could be that somebody will come that is smarter or luckier than everybody else in the last 50 years? Yes. Is it likely? Probably not. Because I'm the smartest person in the world now. There's probably a lot of people smarter than me. There's a ton of people. But it could happen. But in this classroom will prove it, right? And hey, if you prove that P is not NP, then you'll be in history books, right? But if you prove that P equals NP, hopefully, right? You prove it by actually giving an algorithm, right? Then you'd have improved mankind tremendously. It's a lot to go. I don't know if it will happen, but by all means try, right? So if it is, then we have really efficient algorithms for 3SAT and TSP and all those things, right? It would be amazing. We have tons and tons and tons of optimization problems that would be immediately doable, which is amazing. You still need the human factor, but I conjecture there is no good algorithm for traveling salesman problem. That's Jack Edmonds, right? It is possible, but I do not know. Maybe. Tarjan, a bunch of other people saying no. Well, some other mathematician, tell you the truth, I don't know any of those guys except for Tarjan, right? There is this other mathematician that says, no, I think you can, right? Every year-ish, yeah, this is actually funny, right? They had a celebratory dinner, and then they realized that they had made a mistake in the proof. Every year or so, there is a paper on this stuff that becomes widely publicized because they believe that they will do it or not, that they have proved it, and every year we get disappointed. Now with the internet, right? Before it used to be just those two guys having a celebratory dinner. Now you get preprints and stuff on the internet until somebody discovers that no. We had Fermat's last theorem, right, was famous for about 50 years, right, before we Ramanujan proved it. So could be.
Do you ever hear about George Danzig? I think is his name.
For the
Statistician. He came to, this is a true story. He came to class late one time. The professor had written three problems on the board. Two of them were for homework. One was an example of a theorem that they have not proved. That was part of the homework, turned it in, and turned into his PhD thesis. Never know.
You never know. If you prove that they're equal and you come up with an algorithm, I want to invest in your startup. Now, there are possibilities that don't seem that cool, right? Well, maybe P is equal to NP, but you have some other stuff that's still impractical, right? Maybe there is order of n to the 100 or n to the 1000, and then, yeah, it's polynomial. I feel better about myself, but I'm still not going to solve it, right? So those kinds of things could happen. It could also be the other way around, where P not being to NP, but we actually find a really good algorithm that works for NP. It's just slightly better, slightly worse than poly, right? We could also find that we can't prove it. Maybe we will prove that no, we cannot prove it. There are things that we cannot prove. Most of mathematicians now think of Zermelo-Fraenkel axiomatic set theory as how you prove things, and so maybe we can't prove it either. So we are doomed. The Millennium Prize has $1 million for solving it. So if you do, you also become an instant millionaire. And just out of interesting stuff, right? By the way, a bunch of, I think the Simpsons at least, right, have MSs and PhDs and stuff like that, right? Which is amazing. So they actually embedded that stuff. I don't know if there is an overlap between The Simpsons and Futurama.
It's the same dude, right? That name, the writer's the same.
Which one?
At the bottom where it says copyright 1990 Mac Groening.
Oh, but that's
It's the same guy who made both.
okay. The group of writers for actually The Simpsons is the one that I knew, right? Has more PhDs than more places you would think, and yeah, there's a bunch of places. We don't care, but in Princeton, on the wall, they have it. So, slightly more interesting stuff. We have polynomial transformations, and we are going to find NP complete. We have a Cook polynomial transformation. Problem X reduces to problem Y. If arbitrary instances of problem X can be solved using polynomial number of standard computational steps plus polynomial number of calls to an oracle that solves problem Y. That's what we have been using. Right? On the other side, we have actually we have been doing transformation that goes both ways, right? Polynomial CARP transforms if given any input x to the problem x, we can construct an input y such that right, both the construction and the size are polynomial on x, such that x is a yes instance of x if and only if y is a yes instance of y. Basically, the polynomial transformation has only one call to y, as opposed to a polynomial number of calls to y. And I think all of the ones that we showed were like this, and most of them tend to be like this, right? So you just transform it and solve it. But can I do more calls to y, and would that help me, right? And again, we don't quite know. Now, cool thing, the NP complete class of algorithms is a problem y which is in NP, and you have the property that for every problem x in NP, x reduces to y. What does it mean? Notice that there is an equal in here, right? So what I'm saying is that y is the hardest possible NP problem. It's not the hardest because there is a bunch of them that are equally hard. So we have this bunch of really hard NP problems. Those are called NP complete.
How do they determine hardness per se?
It's not hardness, right? It's can you transform it, right? So if I have a polynomial transformation, and what they are doing is you have a polynomial transformation from every NP problem into this one.
Okay.
So you can't be harder than this.
Like, say there are 50 NP complete problems, and that means that all the other NP problems can reduce polynomially to the NP
Exactly.
set.
Yes.
Okay.
And in theory of comp, you actually prove basically there's an infinite number of NP complete problems. There is because when you look at them as strings, right? Like when you look at them as strings, it's just strings and subsets of sets of strings. A problem is just a subset of strings. That's all it is, right? So you're going to say yes or no, right? So over there you can prove those kinds of things, and you will prove them, or at least see the proofs in theory of comp.
Okay.
So some of you were discussing that class. Eventually you will get to that proof, which is incredibly cool and horribly useless. But it's actually not useless, right? I mean, knowing that a problem is NP complete is actually very, very useful, because you know that you're not going to solve it, that you need to go to approximation algorithms and those kinds of things. It's actually not a death sentence. And so if we have NP complete problems, right, any one of them, right, if any one of them was polynomial, then we would show that P equals to NP. Because all the NP problems polynomially reduce to that. Is there a natural set of NP complete problems, right? I mean, we tend to see them as this is what I want to do, and I prove that it's NP complete. But is there something in a mathematical, in a fundamental sense, that puts them together other than somebody wanted to solve it, right? But circuit satisfiability is another problem. It is similar to SAT and 3-SAT and those things, right? Given a combinatorial circuit built from AND or NOT gates, is there a way to sort the circuit input so that the output is 1? That is exactly satisfiability, right? That was the first one that was proven to be NP complete. We know that it is in NP because we have a fixed number of inputs, right? We could represent that with a string. Now, any other algorithm, right? We know that circuit types in NP. Now, any algorithm that takes a fixed number of bits n as input and produces yes or no can be represented by such circuit. And the interesting thing is that if the algorithm takes polynomial time, then the circuit is going to be polynomial time. Any problem on NP has a polynomial time certifier with the restriction that the length of the witness is less than or equal than P of S for some polynomial P. So we would convert this algorithm as a circuit with S plus P to the S, or P of S input bits. Basically, not that one. Oh, it is that one. You're the man. If you could store, right, the information of S and T, right, just this S's and T's, right, if you could store it on a circuit, that would be what this circuit would do. And given that we know that if the number of bits is polynomial, then the circuit is of polynomial size. We can build a circuit that corresponds to the algorithm for satisfiability. So to the NP certifier. And so every NP complete problem would have a corresponding circuit. Isn't that cool? So this would be a circuit that does you have an independent set of size 2 given all the combinations of n and 2, right? So I'm going to have these are the edges. These are all the pairs, right? And these are the vertices, right? I can basically build a circuit that would give me whether the set is of size 2 and this would give me, have I chosen edges, right? Have I chosen both endpoints of one edge? So this horrible circuit would give me an independent set of size 2. Isn't this horrible?
Yes.
Yeah. Well, 5 minutes. Let's look at it. Okay.
Was it just generated arbitrarily, or is this specific
It's
circuit
specifically for this graph.
like it was generated for that particular graph?
Yes.
I guess I don't understand the generation portion.
Okay. Add one input per node. We have 3 nodes. Those are at the right? U, V, and W. And then add one input per possible edge, right?
What do you mean by possible edge?
You have U, V, and W. What could be your edges? This is undirected. So you can have an edge from U to V, and one for V to W, and one for W to U. And that's it. There are no more possible edges, right? So that's why it's the pairs, right? And so there is an edge from U to V, so we'll have a 1 for the UV node at the very left. Here. There is no edge from U to W. There is an edge from V to W. Right? Now,
what about the ands and ors leading up to the top of the graph?
well, this stuff, right, is it a set of size 2? Right?
Meaning you have a 1 and a 0.
I have 2 1s and 1 0 in
2
here.
1s and 1 0, or 2 zeros and 1 1.
No, it's size exactly 2. 2 1s and a 0.
Why wouldn't 2 zeros and a 1 be considered a set of size 2?
2 zeros and a 1 is a set of size 1, not size 2.
0.
Here, these are the vertices. A 1 means that I chose a vertex,
Okay.
right? So I need to choose exactly 2 of these guys.
So it's the set would be like UW, VW, UV,
Exactly.
not necessarily 1 0.
But UV is 1 1 0.
Yeah.
Right? And you could actually, if you remember your architecture or your logic, right, come up with the circuit on your own, right? You basically, but it's an and of 2 of them, right? So either these 2 or these 2, right?
Cannot be UV, or you already have UV, yeah?
Yeah, why couldn't you have all 3 of them?
Because you need a knot on the top left.
No, but here, just set of size 2. That would actually work, right? All 3 of them.
U and W is the only one that works,
Like, if I choose U, V, and W, that would make all these 3 hats true, right? Which would make this hat true. That's an OR. Make this hat true. And that's not a set size 2, that's set size 3. This should be XORs.
I forget, is that the dot being and or I forget, like U dot D?
That's just the, is there an edge between U and B?
Okay,
That's neither and nor or.
so there's not a, so.
If this was really set of size 2, then this should be XORs. Oh. This is really telling me set of size at least 2. If you want to, right? And then this guarantees that I cannot choose 2 edges of the same piece. Isn't this cool? We'll continue talking about it on Monday.